Chapter 7, we're going to focus on these things called symmetric matrices. And we're going to do stuff like diagonalize, symmetric matrices, and we'll see some important aspects that come out of that. What's a symmetric matrix? By definition, a symmetric matrix is just going to be a matrix where the transpose is equal to the original matrix. And that kind of makes sense. If you take the transpose, you switch the rows and the columns, and then you get the exact same matrix. And so that's symmetric about the diagonal. So if you draw a line down the diagonal, it doesn't matter what the diagonals are, but the numbers around the diagonals should be symmetric in that if you fold this matrix along the diagonal, you'll get the same numbers. So that's a symmetric matrix. If we diagonalize a symmetric matrix, there might be some interesting properties that might come up. The fact that they're symmetric. How do you diagonalize a matrix? You remember? Probably. Let's say it was on the final exam where they ask you to say diagonalize a matrix. Yeah. That's the determinant. Oh, man, that was a long time ago. Keep in mind. I felt like I was on Christmas break already. Didn't want to come back anymore. Yeah, what is that called? Yeah, eigen stuff. And you find your P and D. So let's try to diagonalize this. So first we have to try to find the eigenvalues, and then we find the corresponding eigenvectors, and then we create our P and D or whatever. So to diagonalize, oh, so to diagonalize, remember it's P, D, P inverse, or maybe inverse first. I forgot where the inverse was. And D is your diagonal matrix. The diagonal matrix is a matrix with just zeros everywhere except for the diagonals, and the diagonals are going to be your eigenvalues. And P would be a set of column vectors that come from the eigenvalues, which are the eigenvectors. The eigenvectors, P is going to be a matrix full of eigenvectors, and you just have to match them all up. So let's find the eigenvalues. Let's do it by hand because it seems like we're going to need some practice for the final. So it's going to be a minus lambda I is what we need, or the determinant of that is what we need. So we need to subtract. When we do a lambda I, remember it's just the diagonal that's going to get subtracted because the I, the identity, is just the ones in the diagonal. So it's 3 minus lambda, negative 2 and 4, negative 2, 6 minus lambda, 2 and 4, 2 and 3 minus lambda. And so you need to expand along either the one row or one column. Let's expand. It doesn't really matter. Let's expand through the first row. So we got 3 minus lambda. And then cross out the first row and the first column. We need to find the determinant of 6 minus lambda, 2, 2, 3 minus lambda. So remember the alternating positive, negative, positive. So the first one was a positive. We can even put a plus sign here if we want. The next one's going to be a negative, expanding on the, did I say row or column? Doesn't matter because it's symmetric, right? So let's go over here. So we got negative 2, so minus, and then negative 2, and then minus 2, 2, 4, negative, or 3, minus lambda, plus, and then at 4, we got negative 2, 6 minus lambda, 4, and 2. So in our last one, cross out the last column, and then we get this submatrix. All right, so now we are looking at determinants of 2 by 2 matrices. Shouldn't be too bad. We have a 3 minus lambda times 6 minus lambda, 3 minus lambda, minus 2 times 2 is 4. Let's just put a plus here with a negative and negative, and then negative 2, 3 minus lambda, minus 8, plus 4, and then we have a negative 4, minus 4 times 6 minus lambda. Okay so far? I hope. So let's do a lot of foiling out. Let's just distribute for now, and then let's continue to do more algebra here. 3 minus lambda, 6 minus lambda, 3 minus lambda, minus 4 times 3 minus lambda. And 2 times negative 2 is negative 4. 3 minus lambda. 2 times negative 8 is negative 16. 4 times negative 4 is negative 16. Minus 16, 6 minus lambda. Boy, it's a lot. So let's FOIL. We got 18 minus 9 lambda plus lambda squared minus 12 plus 4 lambda minus 12 plus 4 lambda again. Negative 16, negative 16, 32. This is 96. Lambda. All right, so we got one more distribution to do. 18 times 3 is 54 plus 16, thank you. 54 times 3 minus 27 lambda plus 3 lambda squared minus 18 lambda plus 9 lambda squared minus lambda cubed. So as we can simplify that, let's collect all the lambdas. 1, 2, 3, so that's 4, 4, and 16, 24. All the constants, they're all negative. 6, 2, All right, so we got minus lambda cubed and the lambda squareds. It's 12 lambda squared, and then is it? Oh, there's another one. $12? And it should just be 1 lambda cubed. All right, the lambdas, 24 minus 18 minus 27, 21, negative 21. And then 152, 54, 98, negative. Set this equal to 0 and hopefully we can factor. Can we factor? No, because it's a cubic. Just plug it. I should have plugged the whole thing from the beginning. Not on the test. Unless it's like there's there's no constants and then you can factor out an x and then it'll be a quadratic. So let's see, or solve. Let's just say solve. And let's use x. Oh, we can use factor. Let's factor. Look at that. Four, 9, and 2 is. Oh, we could have figured that out. Yeah, 98. It's only divisible by. I guess it's divisible by 3. No, it's not divisible. It's divisible by 2. And then when you divide it by 2, you get 49. So your only choices would have been 2 and 7s for your nice factors. We should have kept thinking about it some more. The constant. If you take a look at the constant and see if you can factor that. Yeah, because the way you get that last number is multiply a bunch of constants. And so if you are able, if this is factorable, then your factors will have either a 2 or I guess 2 divided by 98 is 49, so 2 and 7s. And if that doesn't work, then the chances are you're not looking at a whole number. You might be looking at a fraction or maybe even looking at a complex number. But you're guaranteed at least one real number here. All right, we have x equals 2 or lambda. Lambda is equal to 2 or negative 2. And then lambda is equal to 7 with multiplicity 2. And remember, I used to call it algebraic multiplicity. say that this is a repeated root. And so when we find the eigenvector for this, we hope to get two linearly independent eigenvectors for 7. So let's try to find the eigenvectors now. Say it again. No, it shouldn't. I mean, the negative will be there if we divide, since we're setting it equal to 0, we can divide by -1 and it's all gone. All right, let's find the eigenspace for lambda is equal to -2. Lambda equals -2. And so we have to say A minus, we want to find the null space of A minus -2i. So we basically add 2 to the diagonal. So I need to take a look at what that vector looks, or the matrix. 3 plus 2, -2, 4, -2, 6 plus 2, 2, 4, 2, 3 plus 2. All right. So this is going to be a 5, -2, 4, 2, 8, 2, 4, 2, and 5. We want to do some row reducing. Maybe we can switch the second and first rows and divide by a 2. So I'll do a couple of steps. That's a coincidence, the diagonal being symmetric at this point. So first, I'm going to take row 2 and divide it by 2. Like that. Okay. So let's get rid of that negative sign, might as well. Row 2. And then also I'm going to switch row 2 and row 1 after I do that. Row 2, switch with row 1. So my second row is going to be my first divided by 2. So that's going to be 1 divided by -2. So the change the signs. And then I have a 5, -2, 4, 4, 2, 5. And then this way I can multiply the first one by 2, row 1 by 2, add it to row 2, and multiply by -4, add to row 3. So that'll give me zeros for my first column, the rest of my first column. All right, 2 times -2 is -4. -4 plus 8 is +4. 2 times 4 is 8. 8 plus 2 is 10. -4 times 5, that's 0. -4 times -2 is +8. +8 plus 2 is 10. And 4, -16 plus 5 is -11. That doesn't look right. Oh, I need to be looking at this. Yeah, sorry. I need to go from here, multiply. Yeah. Boy, I messed this one up. Oh, that one's right. So -5? That's better. All right, -5, +5, 0. -5 plus times -4 is +20. 20 minus 2 is 18. +5 and 4 is 9. All right, now with the -4, -4, -4, +16. 16 plus 2, 16, 17, 18. 4, positive, so it's +4 plus 5 is 9. So you see that the second and third rows are the same, so we can just imagine wiping out this thing. So that's going to give us a free variable here. And then x2, well, 18 x2 is equal to -9 x3. So x2 is going to equal a -1/2 x3. And then x1 is equal to -4 x2. Oops, bring that over to the other side. +4 x2, +1 x3 is equal to 4 times -1/2 x3 plus x3. So this is -2. -2 plus x3 is -x3. So x1 is equal to -x3. Oh, I hope I did that right. So our x vector here should look like -1 x3, -1/2 x3, and +1 x3. Yeah, so we can. Yeah. Oh yeah. So we could just multiply everything by 2. So our x vector for lambda is equal to 2, -2. Can be positive, or let's keep it negative. -2, -1, and +2. So that's a good eigenvector. Yeah. Uh, yeah. In general, we might do something else with these eigenvectors, and so it might be nice to not be dealing with fractions. All right, that was hard. Should we just use a calculator now? You guys got the general idea. So if I try x equals, or lambda is equal to 7, I should get 2 free variables after I reduce, right? And then you're going to get 2. All right, so let's just put it into Wolfram alpha then. Wolfram alpha. Well, where's Wolfram? So eigenspace, maybe space. I don't know. I forgot the commands. Let's work it out here. 3 minus 2, 4, -2, 6, 2, 4, 2, 3. Uh-oh. Did I miss a comma? try eigenvalues. There we go. So, all right. So we got the same numbers, fortunately. We got the same eigenvalue that they got. And if we were, again, if we were to do this for lambda is equal to 7, we would get two eigenvalues. We get two free variables, and you see like the zeros where those happen. And so there's going to be some free variables popping up. And then these are all linearly independent. Um, okay, so the diagonalization for this, there's a bunch of different answers, but as long as you're consistent with your D and your P, then you should be okay. So for D, that's the easy one. We can just write it the way we're seeing it here, or we can write it with -2 first. It doesn't matter. So let's do 7, 7, -2. In the diagonal, 0 everywhere else. So this is your diagonal vector. And then your P would be, you need to have the corresponding eigenvectors. So it turns out that V1 and V2 can be, since 7 is the same, it doesn't matter which one is which. So let's just write them in order. So we got the first two columns, and then the last column has to be corresponding with a -2, -2, -1, and +2. So if we were to multiply this with the inverse also, then we should get the original D. Yeah. 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 So another way to write this is your D could have been -2, 7, 7, and then just make sure you write your P with a -2, -1, +2 first. Yeah, your P and your D have to correspond to each other. So, any questions? Yeah. If you had, mm-hmm. Yeah, and then you'll have the eigenvectors corresponding. Okay. Any questions? This is not new. It feels like it's new. Only because we had like the whole week off, and so feels like you've seen it before. Yeah. Well, when you plug it in, what happens is that you're going to get, instead of one free variable like we got here, you're you're going to get two free variables. Yeah, you get two rows of zeros. It'll end up. And so you can adjust your x1 to be whatever you want. Yeah, so if you don't have two vectors for this, which we've run into, then it's not diagonalizable, which could happen. Yeah. Um, I don't know if that's the rule for the inverse matrix theorem. Yeah, but then to relate it to being invertible, I mean, this is matrix is probably invertible, but I don't know if that follows here. I guess it is invertible. So I think if it has, no, I better not say anything because I'm not sure. So I'll need to take a look at the inverse matrix theorem with the eigenvalues and eigenvectors. I think if it has 3 linearly independent eigenvectors, then it's invertible. But I'm not sure. So I'll take a look. Yeah. Well, we just diagonalized a matrix that was symmetric to begin with, and we don't know what this means yet. I'm looking at it. I'm not making any, there's nothing that jumps out right now. But we'll see what happens. There must be something. Yeah, symmetric is just now, another property of a matrix. What? The more you know. It turns out that section 6.6, if you have a random matrix A, that's not necessarily a square matrix, and you multiply A transpose times A, it turns out that that's going to be symmetric. So that's an interesting fact that we didn't go over, and maybe it might come up again. So now let's take a look at this this theorem. Oh, I actually have a proof of it too. That's rare. All right, if you have a symmetric matrix, then any 2 eigenvectors from different eigenspaces are orthogonal. And here's a quick proof of it. Let V and V1 and V2 be eigenvectors that correspond to different distinct eigenvalues. Then the dot product of that, well, they're taking the inner product, but before they take the inner product, they scale one of them. And so that actually is equal to the matrix times the vector. And then there's all this other work over here that shows that they're going to be by hand. I was gonna say a proof of something isn't necessarily, you don't think about it by hand. It's by brain because it's not a calculation thing. But in the test, no, I'm not gonna ask you to prove it. All right. Well, this just says that the last part says that V1 dotted with V2 with a constant outside is equal to V1 dotted with V2 with a different constant outside. And if those things were equal to each other, then, well, the constants are non-zero because they're eigenvectors, and then so V1 and V2 must be equal to 0. So it just says that they're orthogonal. So that's the official proof of this. But let's take our example that we got. Sorry, I'm going to come back to this page. But let's just take the example that we got, and let's just take a look at the eigenvectors. So the proof is up there. This is more of a justification. If we take a look at this, remember, these two came from lambda is equal to 7, and this came from lambda is equal to -2. Now, if you take the eigenvector from lambda is equal to -2, and then check that with the other two vectors, you'll see that v1 dotted with v3 is going to equal to 0, and v2 dotted with v3 is also equal to 0. They come from two distinct eigenvalues, the -2 and the +7. It doesn't say anything about coming from the same eigenvalue. So in this case, this is not equal to 0, is it? It's equal to -1, but more importantly, not equal to 0. So if you're within the same eigenspace for the same eigenvalue, then you're not guaranteed that it's, those vectors are going to be orthogonal. Of course, you can make them orthogonal by doing the orthogonalization process, and then you'd be orthogonal to everything. But in this case, these two, according to the theorem, if you have two distinct eigenvalues, then the eigenvectors that come from those eigenvalues are going to be orthogonal. All right. So yeah, if we want to make the whole thing orthogonal, then we can just orthogonalize v1 and v2, and then since v3 is already automatically perpendicular to v1 and v2, then v3 is going to be perpendicular to whatever new orthogonalization we come up with. All right. So that's an interesting property. So now we're using the stuff from eigenvalues and eigenvectors, and now we're relating it to orthogonality. So symmetric matrices are allowing us to do these things. So speaking of diagonalization and orthogonalization, a square matrix n by n matrix A is said to be orthogonally diagonalizable if there's an orthogonal matrix P with a P1 or P inverse equal to P transpose and a diagonal D such that we can rewrite our matrix into P times D times P transpose, which is the same thing as P times D times P inverse. Such diagonalization requires n linearly independent orthonormal eigenvectors. Well, I don't know. Is it?
Because that's the eigenvectors be orthogonal to all the eigenvectors from other eigenspaces. But since two of our eigenvectors there come from the same eigenspace, that means they're not orthogonal. So that's what they're going to be orthonormal, but they're not orthogonal.
So they're not orthogonal, but can we make them orthogonal? Oh, God. Why, yes, we can. So, that's a good question. Let's soak in Alan's question and see if we can understand. So, we have V1 and V3, V2 and V3 are orthogonal, but unfortunately V1 and V2 are not orthogonal. And so this definition says that if we have 3 orthonormal bases or orthonormal vectors. So right now they're clearly not unit length, so they're not normal vectors yet. They're not normal vectors. There, two of them are orthogonal, or two of them are not orthogonal, however you want to say that between the three vectors. So if we can construct 3 orthogonal vectors and make them and normalize them so that they're unit length, and then assign that to be our p vector, then this vector or this matrix is actually orthogonally diagonalizable. So let's see if that'll work. So the trick, remember, is that these two are not equal to 0, but we can make a projection. We could do some sort of projection thing. Oh man, do you remember that? How do you do the projection? What? Well, let's leave this one alone. So, okay, here's the picture right now. Actually, I don't know how this picture looks like. We can generate it, but let's just say it kind of looks like this generally. Um, I have V1 and V2 on a plane where V1 and V2 are not necessarily perpendicular, or in fact, we checked they're not perpendicular. But we know that V3 is perpendicular to V1 and V2. So it's perpendicular to that plane, right? No, we're not. So what we want to do is we want to make perpendicular vectors out of V1 and V2 and forget about V3. V3 is out of the picture. It's not in our space. It's not in our plane. So this is the eigenspace for lambda is equal to 7. This is your eigenspace would be a line for lambda is equal to -2. So forget about lambda is equal to -2 and just focus on lambda is equal to 7. And that's a two-dimensional plane that's spanned by V1 and V2. So I have a two-dimensional plane spanned by V1 and V2, and I want to just create another vector that's going to be perpendicular to V1. I want to make V2 perpendicular to V1. So you remember how to do that. We project it onto V1, and then we find out what this vector is. So it's basically the orthogonalization process, but just with one step. If you remember what that was from 2 weeks ago. So the Graham-Schmidt process says that V, or I think they call it X. I don't know if they started with X and ended up with V or or Y. I don't know. But in any case, let's translate this to V's and X's that we're going to use. So V2, or the new V2 that's perpendicular to V1, it's going to, let's call it X2. That's equal to V2 minus the projection of V2 onto V1. V2 dotted V1 divided by V1 dotted V1. We do that divided by because this is not a unit vector. So we have to compensate for the length and then times V1. They're all vectors. So it should confuse them. Okay. So we have the vector V2 is -1, 2, 0. V1 dotted V1 is 2. This dot product is -1. We saw that, I guess, already. And V1 is 101. So what am I doing now? -1 plus 1/2. Negative 1/2. So this is -1/2. 2 plus 0. 0 plus 1/2. Let's multiply it by 2. x star 2 is equal to -1 to 1. So x star 2, or even x2, should be perpendicular to v1. Let's check. V1 dotted with x2 star is equal to, well, the dot product of 101 and -1 to 1. So that's equal to 0, right? And this is still on the plane that's perpendicular to V3. So if you take x2 star dotted with V3, you should also get 0. Yeah. Yes, it does matter. Oh, it didn't matter in the dot product, but it does matter when we create our matrix. So thanks. Since we scaled it by 2, so let's make sure we fix that. So -1 for +1. So that's going to be our second vector, and now they're all perpendicular. And to create this orthogonally diagonalizable matrix, we want P to be an orthogonal matrix, which means its columns have to be perpendicular, and it also has to have unit length. So let's write our P. Let's scale each of these things. So we need the magnitudes of V1, V2, and V3. So let's put it off to the side. V1, the magnitude is going to be √2. The magnitude of x2 star, which is what we're replacing V2 with, would be 1, 16, 1. So that's square root of 18. 18. And then the magnitude of V3 is 4, 4, this one 9, so that's 3, right? So those are all the square roots. So let's write each of these things divided by the magnitude. So 1 over √2, 0, 1 over √2. That's the first column, eigenvalue 7, remember? The second column is going to be V2, or x2 star, and x2 star we found to be -1 for 1 with a magnitude of √18. So -1 over √18, 4 over square root of 18. Oh, that's like 2 times 3, right? 2 times 9. Anyways, I'll just keep it a square root of 18. 1, +1 over √18. And then the last one is going to be divided by 3. So a -2/3, -1/3, and 2/3. With your diagonal matrix of 7, 7, -2. Okay. So now let's take this P matrix. Probably should have switched to MATLAB already. 1 over square root of 2. This is going to be tedious. Let's copy this. Let's just do it like this. So that's the first row, or, oh, row. I want to be in rows. -1 over square root of 18, -2/3. All right, 0, 4 divided by square root of 18, -1/3. 1 over root 2, 1 over root 18, and 2/3. All right, what do I want from here? Oh, there, inverse. I want the inverse of that. Ah, what happened? There's an extra 1 square root of 2. There's an extra parentheses here. Oh, I closed there. Like looking for a semicolon in your in your program. What? So if you massage this a little bit, uh, you'll see that it's exactly the transpose. So P inverse, according to Wolfram, looks like this. But if you look at it and divide everything by 6, this is root 2 over 2, which is the same as that. We have 0. And if we divide this by 6, this would be root 2 over 2 again. And then this next one is square root of 2 divided by 6. That's if you, well, it's true. It's a transpose. If we simplified everything here, E transpose is actually going to equal to that, which is what they're saying. Not only that, but if we multiplied these matrices with the diagonal in the middle, we should get the original matrix back. So let's do that. Should have at least used my Mathematica instead of Wolfram Alpha. All right, so it's going to be this matrix dotted with diagonal 7, 0, 0, 0, 7, 0, 0, 0, negative 2. It's not like you can understand that command, but
Oh boy.
let's soak this in for a second. This is the input here, which is P D times P inverse, and some blah, 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 blah work that happened. But look at the answer. Look familiar? Yeah, that's why we use calculator. I mean, if it's a 2 by 2 matrix, then it should be doable on the test, right? Like a final exam. Not to go backwards, but to show that this is actually true. So what's the power of doing this? I don't know. It's fun. But now we got orthogonal matrices to deal with. We have the P matrix, right? And when we first did this problem, the same problem that we're looking at, all we did was we diagonalized this and we ended up with a P and D matrix, right? Which is good. But now somebody wanted for some reason, they said, oh, I wish P was an orthonormal matrix. And so somebody else said, okay, well, let's see if that'll work. And it turns out that if you can create an orthonormal matrix P that is going to make this a diagonalizable matrix where instead of just a regular P matrix, we have an orthonormal matrix. Now we know how to find the inverse quickly because the inverse is just a transpose. If this is an orthonormal matrix, we automatically know that the inverse is a transpose, and so that's easier to find and compute. And now we diagonalize this with orthogonal matrices, so this is orthogonally diagonalizable. Cool? No, it's not. Yes, it is. Yeah, it's kind of cool. Hopefully, my goodness, hopefully it's useful. Otherwise, we're just wasting our time. Another tool. That's what linear algebra is. You got all these tools you might never use again, but one of these days you're in your engineering lab or you're doing some computer graphic stuff, and then all of a sudden you need to, I need to figure out an orthogonal matrix. Oh, good thing I paid attention in Professor Lapuz's class because now I can find it. And then you take out Wolfram Alpha or MATLAB and just punch it into the computer, right? Because, I mean, in real life, you wouldn't do things by hand unless you're out in the middle of nowhere. Yeah. What if your plane crashed and then you're out in the middle of nowhere and then you needed to, I don't know, diagonalize a matrix? Oh, yeah, there you go. That seems like a good game. All right, here's the second theorem in this section. If you have an orthogonally diagonal matrix, or A is orthogonally diagonalizable if and only if A is symmetric. Oh, so you can only do this for symmetric matrices. Well, that's why symmetric matrices are important. Because now you can orthogonally diagonalize it. All right. What else do we have? Oh, there's an example. Oh, here we go. Spectral theorem. This is going on a new page for sure. So spectral theorem for symmetric matrices. So this is a theorem that they can use for symmetric matrices. If you have an n by n, you have a square matrix that has following properties. First of all, it has n real eigenvalues, even counting multiplicities. The dimension of the eigenspace matches its multiplicity, and the eigenspaces are mutually orthogonal. Then A is orthogonally diagonalizable. B, the dimension of each eigenvalue equals the multiplicity. Eigenspace for the eigenvalue equals the multiplicity. So what that's saying is that it's the same thing that we did in our problem where we had lambda is equal to 7 eigenspace. So lambda is equal to 7 has algebraic multiplicity of 2, and so the eigenspace should also be two-dimensional. When we first started, I don't know if you want to look back in your notes, but when we first started doing eigenvalues and eigen vectors, we did a couple of problems where it has an algebraic multiplicity of 2, but it only had one eigenvalue, eigenvector. That's sometimes called a geometric multiplicity when we were talking about eigenspaces. So you have an algebraic multiplicity of 2 and a geometric multiplicity of 2 as well. And it turns out that if you had a matrix where you had an eigenvalue with an algebraic multiplicity of 2, but you only got one eigenvector out of it, which means the eigenspace has geometric multiplicity of 1, then it didn't match. So it wouldn't be orthogonally diagonalizable according to this theorem. Okay. Now, this is a spectral theorem, but it's only like the beginning of a theorem that we need to dive into a little bit more. Yeah. Because it put weights it puts weights. I don't know why it's called spectral theorem now, but there is a follow-up part to this, um, in that you can decompose decompose a spectrum with the different vectors that you're dealing with, and then all you're all you're really looking at is the coefficients of each of those decompositions, and then that's going to be your eigenvalues and eigenvectors. So let's just let me get this down here. So if you're able to write your matrix and diagonalize it, where the columns of P are orthonormal eigenvectors. So if you had one of those that doubled up, then you make sure you're orthogonalizing it. And you have the corresponding eigenvalues, lambda, in a diagonal matrix D. So if P inverse is equal to PT, then you can rewrite your A as, now the P is going to be a collection of column vectors U1 through UN, and then so the P transpose, which is the P inverse, is those same collections. And then since you're multiplying it with a diagonal matrix, you're essentially just, if you do the multiplication, it's just lambda times the first column, lambda 2 times the second column, etc. And then when you multiply this through, you're going to get this lambda times the dot product of those vectors. So representation of A is called a spectral decomposition because it breaks A up into pieces determined by the spectrum of A. Note that U1 times U1 transpose is a projection matrix, in the sense that it looks like the inner product, right? But it's actually, the inner product is actually U1 transpose dotted or times U1. And if you switch the order, remember what happens? It becomes like the outer product, and it becomes matrices. So let's take a look at that same example that we've been dealing with. Do you remember what it was? Let me copy this part down. Whoops. All right. So according to our spectral decomposition, um, this is supposed to be equal to A is equal to, let's do this in a different color. A is equal to lambda 1, 7, times the first vector here, 1 over root 2, 0, 1 over root 2, times the transpose of that vector, plus 7 times something else, times plus negative 2 times something else. So these are products, outer products, but let me just show you what happens here if we take a look at this vector, or this outer product. It turns out that this is going to be a matrix, right? So the matrix is going to be 1 times this is 1/2, and then first row, second column, first row, third column, 0, 0, 0, and 0. It turns out to be a full-blown matrix. So this is called a projection matrix in the sense that for x and Rn, if you apply a vector to that matrix, it's going to be an orthogonal projection from that vector onto the subspace spanned by u's. So this is a special projection matrix that projects any vector in R3 onto that V1 or U1, or I think call it V1 vector. And then we can do the same thing and find these other orthogonal projections. Okay. And if you add all this up, it should add up to the original matrix. So, we had the simple decompositions. We decomposed our matrix into LU decomposition, and then we got a little more complicated with a QR decomposition. Now we have a spectral decomposition where we decompose this matrix. Oh, and then we also decompose the matrix into the orthogonalization, the PDP inverse matrices. So now we're expanding our decomposition even more. And it works if you have an orthogonally diagonalizable matrix, you can decompose it into the spectrum. And that will work if you have a symmetric matrix. All right. Take a breath. Go back and remember your linear algebra stuff. Oh, you guys know that the makeups are online? They're due on Wednesday. I was supposed to give it to you before Thanksgiving, way before Thanksgiving, and then I was going to be due today, but I forgot to give it to you. So now you have today and tomorrow. It'll be due this Wednesday. For the test, any of the tests, one of the tests. You could turn something in and we'll see. Give you half credit.